Subtopic 1.1 Rate Law. The learning outcomes for this video are: A. Define reaction rate. B. Write differential rate equation. D. Define rate law, order of reaction, and half-life. E. Write rate law with respect to the order of reaction. F. Write the integrated rate equation for zero, first and second order reactions. Reaction rate. Reaction rate can be defined as the change in the concentration of reactant, or product with time. Consider for the reaction, reactant A to product B. We can write rate as delta concentration over time.
The rate of a chemical reaction is a measure of the rate at which the products are formed, which is equal to the rate at which the reactants are consumed. This is taken as the change in concentration divided by the change in time. Hence, the rate of the reaction has units of moles per liter per second. In the reaction, reactants P and Q give products R and S. The relative rate for this reaction can be expressed in terms of the decrease in concentrations of reactants and increase in the concentrations of products as -1 over P, delta P per delta T, equals to -1 over Q, delta Q per delta T, equals to +1 over R, delta R per delta T, equals to +1 over S, delta S per delta T. Note the minus sign for the reactants, which is necessary because the concentrations of reactants decrease with time, whereas the concentrations of products increase. The numerical value of the rate will vary according to the number of moles of the reactant involved in the stoichiometric equation versus the number of moles of the product. Let us look at an example. In the reaction between dichromate ions and iron II ions in an acidic medium, the stoichiometric coefficients are respectively 1, 6, 14, 2, 6, 7. The rate of appearance of iron III ions is 6 times as great as the rate at which dichromate IV ions are consumed. The rate of this reaction is minus the change in the concentration of dichromate IV ions per change in time, which equals plus the change in the concentration of iron III ions per 6 times change in time.
Rate law. The rate law is an equation that relate the rate of a reaction to the rate constant and the concentrations of the reactants raised to some powers. Rate constant, K, a proportionality constant for a reaction at constant temperature.
Let us consider a reaction involving reactants A and B. The rate equation for this reaction takes the form: the rate is proportional to the product of the concentrations of A and B raised to powers m and n respectively. The proportionality constant K is called the rate constant. The exponents of the concentrations m and n are called the orders of reaction with respect to A and B. They are determined experimentally.
Order of reaction. Defined as the power to which the concentration of a reactant is raised in the rate equation. The order of a reactant is not related to the stoichiometric coefficients of the reactants in the balanced chemical equation. It can be only determined experimentally. Overall order of reaction, sum of the order of reaction for each reactant in the rate law. Half-life. The half-life, T-half, is the time required for the concentration of a reactant to decrease to half of its initial concentration.
Now, let us derive the half-life equation from the concentration time equation of a zero-order reaction. The half-life is the time taken for the concentration of the reactant to fall to half of its initial value. Substituting AT by A0 over 2 in the concentration time equation, gives a final equation for the half-life as follows. T half equals A naught per 2K. Hence, the half-life of a reactant increases as its initial concentration increases. We can derive the half-life equation for a first-order reaction from the concentration-time equation. The half-life is the time taken for the concentration of the reactant to fall to half of its initial value. Substituting AT by A naught over 2 in the concentration-time equation gives a final equation for half-life as follows. T half equals ln 2 over K, or 2.303 log 2 per K. Note that the half-life of a first-order reaction is independent of the initial concentration of the reactant.
If we substitute the halved concentration of A, we will find that the half-life for a second-order reaction is 1 per K times A naught. This means that the half-life of a second-order reaction depends on the initial concentration of the reactant. Since the concentration of A varies with time, the half-life of a second-order reaction varies with time too.
For a zero-order reaction of the type A gives products, the rate equation is as follows. The decrease in the concentration of A per unit change in time is equal to the rate constant K. The rate of the reaction does not depend on the concentration of the reactant. After integration and multiplication by -1, we obtain the following rate equation. The initial concentration of A minus the concentration of A at time t equals the rate constant multiplied by the time t. The concentration is a function of time, and the graph obtained is linear. The graph of concentration against time for a zero-order reaction has a negative slope.
Suppose that this reaction is first order with respect to the concentration of A. Using calculus, one can show that a first-order rate equation, like this, leads to the following relationship between the concentration of A and time. So, the rate equals the negative change in the concentration of A per change in time, and equals the rate constant multiplied by the concentration of A. Rearranging the equation and integrating from time equals 0 to time equals t gives the logarithm of the concentration of A at time t minus the logarithm of the initial concentration of A equal to minus the rate constant multiplied by the time t. This can be rearranged to give the equation showing that the logarithm of the initial concentration of A divided by the concentration of A at time t is equal to the rate constant multiplied by the time t. The rate equation is the decrease in the concentration of A per change in time and is equal to the rate constant multiplied by the square of the concentration of A. Again, using the methods of calculus, this equation can be rearranged to give the form which is on the screen. Integrating this from time equals 0 to time equals t gives the equation relating the reactant concentration to time for a second-order reaction.